So this is lecture 25, and today is 10th of March 2021. Okay, so let me just kind of refresh your memories from last week that we covered, we introduced friction. Is there are only two things that are very important to remember when it comes to friction problems. One is the direction of friction force. That unlike the way you did the free body diagram in frame analysis, friction force is always opposite to the direction of motion. So you need to identify, based on the given information, the geometry of the problem, what the direction of motion is, potential direction of motion. And once you determine that, then you can obviously easily know that the force of friction is in the opposite direction. So you put it in that free body diagram. The second important concept is that friction problems consist of two types. Either equilibrium is explicitly assumed. So the problem statement tells you the system is not moving, or you have equilibrium, or should not move in whatever ways it is stated. Clearly gives you the information that the system is in equilibrium. The second type is that you do not know. So what is the benefit of that? Or what is the information that you can then assume for this type of problem? If the system is in equilibrium, the friction force is always its maximum value, which is mu times n. In other words, we assume that the system is in equilibrium, but potentially, if it's going to move, would be at the impending motion where the force of friction is maximum. But the second type is that you do not know if the equilibrium is present, or the system may or may not move. So based on that, you find the unknown, which is the friction force. And if at that point of contact where the friction force exists, the force of friction ends up to be less than this, that means system is in equilibrium. If it exceeds that, the equilibrium is violated. So for the time being, we are focusing on these types of problems. So let me do a few more problems, okay? And I start with this example. Okay, any questions? No? So let's go ahead. No matter what, some people still come 10, 15, 20 minutes late. All right, so you have a system that consists of a piston that can move in this slot. The piston is subjected to a force of 100 Newton, okay? At point A in the middle, on this piston, you have attached a rod or pinned to it, that this rod is connected to a device that is basically a color, okay? This color consists of a piston that moves up and down along this rod, okay? And this linkage is connected to that pin to it at point B, okay? So in order to prevent the motion of this piece, cylindrical piece that moves along this rod, we exert a force to keep this in equilibrium. Obviously, if this force is applied in this direction, this linkage would have the tendency of moving this upward. So we apply this force downward, and we want to know what is the minimum P required to keep this from moving up. Okay? So listen to the way that I stated the problem. We do not want this to move up. We want to keep this stay where it is. That means the system is in equilibrium, right? There is no friction here, no friction between these two surfaces, but between this piston and the rod, there is friction, and the coefficient of friction is given as 0.2. Okay? So how do you solve the problem? To find the unknown, which is this minimum P required to keep this in equilibrium, just draw the free body diagram of each piece. This is a frame problem, right? How many pieces you have? You have this piston subjected to this load of 100 Newton. Obviously, this is slides back and forth. So there is a vertical force, and at A, perpendicular to the potential direction of motion. This is a two-force member, is a linkage, pinned here, no load acting along that. So that represents a force at this point, force of AB. And this angle, by the way, is given as 60 degrees. So this is 60 degrees. So the other free body diagram would be the free body diagram of this linkage, force of AB, force of AB, and then the free body diagram of this piston, okay, which is obviously acted upon by this force AB, right? You have an applied load P here, and a friction, and obviously this goes up and down against this rod, so you do have a vertical reaction force perpendicular to this direction of motion. And then there's a friction force that is going to basically resist the motion. But since this piston, due to the action of this force, would potentially cause a motion upward, therefore the force of friction that would develop here would be downward. So I call this F sub B. And given that we want this to stay in equilibrium, we know this F sub B is mu B times NB. So these are the three free body diagram that you have. Any questions? So, like any frame problem, you start solving for the unknowns. Except, as I said, the difference between these problems and other frame problems where friction doesn't exist and you are only asked to find the forces at the joints is that you do not have to find all the unknowns. You only find those unknowns that help you to find the answer to the question or find the unknown that the problem is asking for. So when I start with this free body diagram, I can write both summation of forces along X and Y, but I only use summation of forces along X equal to 0 because that's the only force I want to find. I don't care about this. It doesn't come into picture in this free body diagram where this unknown force exists. All I need is only this force, which is here. So I only find this force from this free body diagram. That means 100 Newton minus FAB cosine of 60 is equal to 0. Cosine of 60 is 1/2. So that gives me F of AB. That comes out to be 200 Newton. Okay. All right. So now I use free body diagram 3. If I write summation of forces along X equal to 0, okay, I can find this reaction force. I need that to find F of B, right? Because you have 1, 2, 3 unknowns here, but this is not an independent unknown. It's related to that. You have 2 unknowns and 2 equations of equilibrium. So I use the first one as summation of forces along X equal to 0. That gives me 200 cosine of 60 along x minus NB is equal to 0. So NB comes out to be 100 Newton. Now I write summation of forces along y is equal to 0. And that way I can find P. How? Just write these, negative P, negative F sub B, which is mu B times NB, plus F AB sine of 60 is equal to 0. Okay? Sine of 60 is square root of 3 over 2. Okay? This one is 0.2. Okay? And this is 100. So I solve for, and of course, f of AB was 200. So I solve for the P from here, and I get P to be 153 Newton. So for keeping this in equilibrium, you need to apply a force of 153 Newton so that this system will stay in equilibrium. Any questions?
When it's a friction problem, do you not need to draw like the forces on the entire free body diagram, like the whole system free body?
The whole system?
Yeah.
Well, the whole system, you cannot have the free body of the whole system because it's an infinite rod. We don't know what the connection here or what the connection is here. So therefore, you only have 3 free body diagram of the 3 pieces.
Okay, thank you.
Sure. Any other questions?
Quick question. So the forces NA and NB, just wanted to check in where those came from.
Here? See, this is a 2-force member, right? So if it is connected to this piston, and you're pushing the piston.
NA,
right?
not N. Like the vertical force on A and the horizontal force on B. NA.
This one?
Yeah, is that like the normal force or?
It's a normal force. This is like a roller, right? So if it's moving this way,
okay.
Right.
Okay, I wasn't looking at it as a roller, but that makes sense. Thank you.
Any other questions?
My question is, how could we assume a normal force without a mass number, like a?
Oh, you do know. You do have a force acting downwards. You see, this is coming here, so it's pushing on this. This doesn't have a mass. Now, the weight of this is 0, but you have a force acting this way on this piece, so it causes a vertical force, right?
Okay.
Right. Any other questions?
Yeah,
Right.
I wanted to ask your reasoning behind why the friction was downwards.
Oh, this friction force. You always need to visualize the physics of the problem, meaning that, okay, what direction this is going to move. If you have this load acting, right, it's going to push this linkage in this direction. So the force is like this, right? So it's going to cause this piston go upward, right? If you have a force acting this way, just forget about P. P doesn't
I see
exist,
it.
right? If P is not there and you have a force acting on this block like this, right? It's going to move it upwards, right?
Yeah, that makes sense. Yeah, I was just wondering how the B that B component. I didn't really know it was a piston. Thank you.
Right. Yeah, of course, because we want to apply P due to the fact that this is moving. But what direction this is going to move before P is applied? It has to move upward because the only force acting on this is this way, which causes an upward motion. Therefore, the friction force is in the opposite direction, downward. Okay. All right. So let's do another problem. Okay. This is a good problem. This is a fun problem. We have, okay, let me draw this first because it requires some artistic work here. So this is the problem that we have. Okay. PG&E has had a power failure. Okay. So they want to send the guy to repair that whatever thing on this pole, on this power transmission line. Okay. This being a very advanced country that we are, that we still have these archaic wood poles that any storm, anytime any slight storm takes place, they just fail and we have to repair them. You know, if you go to even most underdeveloped countries, you don't see anything like this because we don't spend enough money on our infrastructure. But anyway, so that's my philosophical discussion of the day. But this guy works for PG&E and is sent on site to fix the problem. So the guy, he weighs 180 pounds. In order to climb up this pole, he knows he can rely on friction coefficient of his shoes, which are given. So between his shoes and the pole, obviously there's friction, let's say at point C. And the coefficient of friction here, which is coefficient of friction of the shoe, is 0.6. However, he has to attach this leather belt, which is the sort of the mechanism that guarantees this guy stays in place and doesn't fall off due to the friction between the belt and the light pole. This belt wraps around this pole and at point A supposedly rests on this pole and friction is generated between that and the pole, preventing this guy to coming down. We do not know, of course, other dimensions are given, the distance between the point of contact of the belt and the guy's shoes are 4 feet. The thickness of this pole is given as 0.75 feet. The distance between the center of gravity, okay, this is B, this is G, and this guy's tummy is 0.5 feet. Between this guy's tummy and where this belt connects and the pole is a distance of 2 feet. Okay, so this is the geometry of the problem. Now, this guy wants to make sure that PG&E is not giving him a cheap leather belt. So he wants to find out what is the friction force that is required in addition to the friction force of his shoes to keep this guy in place. Because PG&E doesn't care. Being a multi-billion-dollar company, they don't care about the life of their workers or their welfare at all. They try to pay a minimum wage with no health insurance, nothing. So poor guy has to be concerned about his own safety, right? Corporations do not care about your safety. That's the second philosophical discussion of today. So anyway, so what do? We need to find out the coefficient of friction required at point A. How do we do that? Obviously, we need to solve for this unknown. And to do that, you need to draw the free body diagram. I don't want to draw a free body diagram separate from this figure that so artistically I have drawn here. So I will do it over this. We do have the weight of this guy. If this guy potentially, God forbid, slips here, what would be the potential direction of motion? His shoes are going to come down, right? So the motion that may occur at point C would be downward. Therefore, if a friction force exists here, which I refer to as F sub C, would be in the opposite direction, upward. And of course, you have this vertical normal force at C. Obviously, we don't want this guy to fall off. That means equilibrium is presence. Where equilibrium is presence, we know F sub C is related to N sub C is mu at C times N sub C. So these are not two independent unknowns. How about here? Again, if this belt slips, would it slip down? That means motion is downward. So if there is a friction force at A would be upward. And obviously there is also a normal force here. So this is the free body diagram of the whole system. Okay? So with that, let's see if we can solve for the unknown. Because all we know at FA, mu A times NA, but we do not know what mu of A is, right? So there are two unknowns here. So let's write all the equations of equilibrium that we have, the three equations of equilibrium. To start with, I will begin with summation of moments at A is equal to 0. Why? Because I want to find N sub C, because if I find N sub C, I can find N sub A, and I have this relationship, and that gives me, of course, mu A. All right, so if I take summation of moment about A, what do I have? I have the moment generated by N sub C, counterclockwise, distance, vertical distance is 4, so N sub C times 4. The moment by F sub C, this is the vertical distance between this and the point of rotation. So I have plus F sub C times 0.75. Then the moment generated by the guy's weight, which is clockwise, right? Rotating clockwise in that direction, okay? So if it's rotating clockwise, that would be negative. So you have negative 180. What is the vertical distance between the two? Is this is 0.75, this is 2.5. So it's 3.25 equal to 0. All right? F sub C is related to N sub C. Coefficient of friction is given. So F sub C is 0.6 N sub C. I substitute that in here. So I have one equation, one unknown. I get N sub C to be 131.5 pounds. Okay? So I've used up one of the equations of equilibrium. The second one, summation of forces along Y is what I will write. And that gives me what? F sub C plus F sub A minus 180 is equal to 0, right? That's what I have. So F sub C is what? 0.6 times 131.5, okay, minus 180 plus F sub A is equal to 0, okay? So I can find F sub A if you subtract these two, you will see that it comes out to be actually 100 and negative 101.2. F sub A is mu sub A times NA, where NA, I can actually find NA, right? So, but let's just write this equation. I have mu A times NA is 101.2. So this is summation of forces along y equal to 0, right? I have one more equation. Summation of forces along x equal to 0, okay? That would give me n sub c minus n sub a is equal to 0. So n sub a is equal to n sub c, which is 131.5 pounds. If I substitute that in here, I get mu sub a, that comes out to be 101.12 divided by 131.5 equal, that gives me mu sub a, that comes down to be 0.77. So in order for this guy not to slip down this light pole or power transmission line pole, he needs to have a belt, supporting belt, with a minimum coefficient of friction to be 0.77. So what does this guy do? What is the next step? Can anybody tell me? What is the next step? I just told you, right? He would go to his boss, says, I have figured out this is the minimum coefficient of friction that the belt that you're giving me should have, so that I am staying safe and I don't fall off the light pole, right? And then, of course, the boss has to provide him that belt. Any questions about this problem? No? All right, so let's do another one. All right. Any other general questions so far about friction? Okay, the third
The last problem, when you had the normal forces, were those like the maximum normal forces that you could have, or could those be adjusted by like changing the angle of the belt? Like,
what do you mean, these normal forces?
yeah, like if you
Normal
put his legs
forces,
up,
if
like,
you remember, come from what? Where do they come from? Anytime you have two objects sliding with respect to each other, right? Like a roller, right? A roller that is, sliding against this surface. A normal force is generated that is perpendicular to that surface. So the direction of the normal force is always perpendicular to the potential direction of motion. This guy's shoes are sliding along this pole. So this normal force has to be perpendicular to the pole. And the belt is also sliding against this pole, right? So the normal force has to be also perpendicular to the pole. Does it clarify it?
But like, since the normal forces, the only thing in the x direction are the two normal forces, could you like change the magnitude of those by adjusting the angle at which he places his foot? You know, like, since
of course. Yeah, if the guy, instead of sticking his feet against his light pole, put them in an angle, right? The normal force, depending on how that connection is, would be perpendicular to that. In other words, let's assume, hypothetically, of course, speaking, that there was this light pole, but then this light pole has something sticking out, so the guy puts his foot here. So the motion is taking place along this. So the normal force would be perpendicular to that. Normal force is always perpendicular to the potential direction of motion at the point of the contact. of the two objects. Objects in this case being this guy's shoes that is in contact with the pole. So if this is moving in this direction, the normal force would be perpendicular to that. Okay? All right, so let's move on to the next problem. The third problem that I have selected for you is this. You do have a beam. Beam is sort of a mechanism that is connected to a pin at this point B at one end, and at this end is pinned to a disc, a circular disc, okay? And the circular disc is resting on an inclined surface, which makes an angle of 30 degrees with the horizontal line, okay? So let's say the point of contact of this disc with this inclined surface is point C. This beam is supposed to, and of course this disc has a weight. Obviously the weight is exerted, acts through the center of gravity of this disc, which is at the center of the circle, okay? And the radius of this circle is given, or is 0.2 meters. The weight of this disc is, or the mass is given as 35 kilograms, so times g, gravitational acceleration. If it is about 9.81 meter per second squared, that means the weight would be 343.3 Newton, okay? Okay, so this whole system is subjected to a vertical load of P that is acting on this beam at a distance of 0.6 meter from this end and 0.3 meter from point B A, okay? What you want to find out is if this is a sort of a machine that is supposed to hold this load P, okay? What could be the maximum load P that you can apply to this beam without causing this disc to rotate or slip down this inclined surface? So you should be able to visualize this problem, right? You have a load acting on this beam. This beam is pinned to this disc, but you want this load to be such that no motion takes place between this disc and this surface. The maximum load that this beam can carry. So how does this work? Obviously, when you apply a load here, what happens? This disc is going to go move in what direction? What direction this?
At 30 degrees.
No, I mean, what direction this disc is going to rotate? Clockwise or counterclockwise?
Clockwise.
Clockwise is so it's going to move in this direction. So if there is a friction force that is potentially developing between this and the surface here, and by the way, the coefficient of friction here is given as 0.2. So if a friction force develops between the disc and this surface, what direction that friction force would be if the motion is taking place in this direction? Is it going to be this way or that way? Downward or upward? Can anybody tell me? Remember, force of friction always opposes the direction of motion. What is the direction of motion? This way.
Downward.
So
Oh yeah.
the force of friction on this disc would be downward. So this is the force of friction at this point. So let's draw the free body diagram. And of course, you do have, obviously, a normal force N sub C that acts this way. And since this is a circle and point of contact is C, this force of NC would go through the center of the circle, right? You can visualize that. Okay. All right. Any questions? Okay. All right. So how do we solve the problem? To find the maximum force that can be applied, okay, without causing any slippage. Well, it's a frame problem, right? So you need to draw free body diagram of all pieces. So let's do that. This is one piece pinned at this end. So you have these two forces, Bx and By, okay? And this is at this end, another pin connection. So let's assume these are the directions of the unknown forces. And then you have the supplied load P. This is 0.6 meter. This is 0.3 meter. So this is a free body diagram of that beam. Okay. How about the disk? The disk is pinned here. So if these are the assumed direction, at point A, you have A sub Y and A sub X in this direction. At point O, the center, you have the weight of this disk, 3.43.3, assuming that the weight is evenly distributed, is homogeneous material, and so on. And then you have what? You have this force N sub C, and this force F sub F, which is mu sub C times N sub C. So these are all the unknowns you got, right? And this, by the way, is 30 degrees. So if that is 30 degrees, this would be 60 degrees, okay? So these are all your free body diagrams, 2 free body diagrams, okay? So how do you solve? Well, remember, you do not have to find all the unknowns. All you need just to find the unknown that you've been asked to find with finding minimum number of other unknowns, okay? So what I will do, I start with this one. In free body diagram number 1, I write summation of moments about B is equal to 0. The reason for that is I'm trying to find unknown P, but I have 5 unknowns here. Whereas here I have 1, 2, 2 and 3, right? And 4, I'm sorry, 1, 2, no, 3, 3 forces. So I can start with this one, but because of the geometry of it, I cannot find all the unknowns. So I start with, and also not only that, these are not the unknowns that I want to find. I want to relate those unknowns to the unknown that is my ultimate goal, which is P. So I would like to find a relationship first between one of these unknowns and the supplied load, so that when I go to this free body diagram, I can find my ultimate unknown, which is P. Okay? So I will start with this one. And I see that if I write summation of moments about B is equal to 0, I can see that this would be the equation, P times 0.6, taking summation of moment. This would generate a positive moment. And the only other force is AY that generates a moment. This distance is 0.9 is equal to 0 because this force, and this force all go through point B, so they don't generate any moment. There's only this one and this one. So this equation will give me 0.67 P is equal to AY. So I found the relationship between the unknown and AY. I don't care about these. I just quickly go here because I know that I have 3 unknowns and I can find all of them. And now that I have only these unknowns in terms of P, if I find all these unknowns, I can find P. Okay, so in this one, I will start by writing summation of forces along Y equal to 0 first. If I write summation of forces about Y is equal to 0, okay, what do I get? I need to resolve these. Obviously, this is X, this is Y. So I need to resolve these two to their components. So if I do that, this is NC, right? Cosine 60. This is NC sine 60. Here, this would be F of F, okay? Sine 60. And this is F of F cosine 60. So writing summation of force along Y would be N sub C sine 60, which is cosine 30. So N sub C, okay, sine 60 minus F sub F, okay, cosine 60, okay, minus 343.3 minus AY, okay, and AY is 0.67 P is equal to 0. So let's simplify this, okay. F of F, we said is mu sub C times NC. Mu sub C is given. So this is 0.2 N sub C. So I'm going to simplify this a little bit. And this is sine of 60 is the square root of 3 over 2. Cosine of 60 is 1/2. Okay? So I'll just simplify this. I get a square root 3 over 2 minus 1/2 times N sub C is, minus 0.67 P is equal to 343.3. Let me simplify this further. This is, let me do that. I haven't done that yet. So let me quickly do that. You have 1.73 divided by 2 minus 0.5. Okay. So you have 0.365 N sub C minus 0.67 P is equal to 343.3. This is another equation of equilibrium. The same diagram, now I write summation of moments about point O is equal to 0. if I take so much in a moment about point O, this force is going through point O, this force is going through point O, they don't generate any moment. This force is at a normal distance of R, which is given 0.2 meter, generates a moment. This force doesn't generate a moment, this one does. So you have only this one and this one. So I have F sub F generates a moment in that direction. So you get F sub F times 0.2 minus A sub Y times 0.2 is equal to 0. That means F sub F is equal to A sub Y. Okay? This is 0.2 N sub C, okay, is equal to, okay, A sub Y was 0.67 P. So I get 0.2 N sub C is equal to 0.767 P. Okay, I have two equations, two unknowns. Okay, I can solve for P, which is all I need. I don't care about N sub C. I solve for P, and that will give me P of 182 Newton. So the maximum force you can apply to this beam in such a way that this disc doesn't slip down this hill is 182 Newton. Okay. Any questions? No questions? All right. I was going to do another problem in the previous section, but time was not enough. But I hope I can do that problem in this in your section. So let me at least start. If not, I will send you the solution. Don't worry about it. Okay. But let's see if you have any questions first. No? All right. So I have already drawn the problem. This is the problem. You have a mechanism. This is how this mechanism works. It consists of a lever or a linkage that is residing on this roller, and this roller is sitting at a distance of 0.8 from here. This is 0.8 meter. So let me actually fully describe the whole problem first. You have this lever connected to a piston. This piston can go up and down along this rod. This rod is connected to this surface. And on the surface perpendicular to that, you have a roller, okay? And this bar at one end is subjected to 100 Newton force. And at the other end, P is pinned to this piston that can go up and down. The distance from the center of this piston to where this roller is given, 0.8 meter. The angle between this rod and this vertical line is given, 30 degrees, okay? In other words, this is also 30 degrees, okay? This is a problem statement. You want to know if you apply a load of 100 Newton, how much force is required to be applied to the cylinder so that the cylinder does not move up or down, okay? Stays in place. That's it. So we don't know, of course, if you apply this load, if this is going to go move up or down, okay? So we will assume first that it's going to go up. So we're applying the force downward. That means the force of friction would be upward. Okay? So if this is, we again, we draw the free body diagrams accordingly. Okay? So the question is, find P that keeps, okay, that keeps the system in equilibrium. Okay? All right. So based on that assumption, if this piston moves up, right? Moves up. That means the friction force that is acting on this would be what? Would be downward. This is the force of friction. You do have this force P, right? You do have a normal load like this on this piston, okay? And then you do have a force that is coming from this rod at this point, okay? I'm just looking at the clock and I have actually exceeded the time. So unfortunately, I cannot finish this. Let's leave it for the next time. So I'm going to stop here and see if you have any questions.